Okay, welcome back. So, right, what we ended with was the following. So what we have is that if we're looking for a product solution, or a separated solution, you might say, of U, okay, what we did is we said, well, it's going to be some function of space, some function of time, okay. So we know what the time piece looks like. Now we need to figure out what the spatial piece looks like, okay. We have an ODE for the spatial piece. We just need to take a look, start computing, seeing what happens, okay. And so one thing to keep in mind is that, well, C is an unknown constant, okay. It'll be fixed by the initial condition. But the other piece that we're working with is this parameter, this constant lambda, right? And this lambda, if you recall, came in through, we equated, right, kind of this left-hand side of, or I can scroll back up, right? Lambda played in here, and lambda kind of connected these two pieces, right? It was the separation constant, okay? So what we're working with is C is an unknown, but that'll come from the initial condition. Phi is unknown, but we have an ODE for that, as well as boundary conditions for the ODE. And then this unknown lambda is also connected to this phi, okay? So the hope is that if we kind of work through, figure out what the form of phi is, then we can figure out what form lambda must take. Okay? So as I said, so we have some information about phi. It must satisfy this ODE, right? Second order boundary conditions. And so what we're going to do is we're going to solve for phi, right, by kind of standard techniques from ODEs. And then we're also, at the same time, going to figure out what lambda could possibly be. Okay. And so we're going to consider a few cases separately. Okay. So either lambda is going to be positive, lambda is going to be 0, or lambda is going to be negative. And so then keep in mind that, right, if lambda is positive, because of how we've written this number is going to be negative. Yeah, okay. So the first case we're going to consider is lambda equals 0. Here we have this ODE, d squared phi dx squared is equal to 0. So our solutions are just going to be these straight line segments, okay? How do we get these solutions? Well, we can go through, right? Assume there's a solution of the form e to the rx, figure out what r is, plug that in, you get r squared is 0, so you have a double root. So you have the constant term plus x times a constant term. This is the short of it. The technique of plugging in e to the rx, we'll see that a bit more in the next bit. But the point is, right, for this ODE, just as we saw with these equilibrium solutions, we have these straight line solutions. Okay, straight line, yeah, it's the profile of these solutions. Okay. So, yeah. So now the question is, what are the constants A and B? Okay. So if we look back to the boundary conditions, well, phi of 0, right? You plug in the form of the solution, you get A times 0 plus B. We're told that has to be equal to 0. Okay. And likewise, phi of L is going to be A times L plus B coming from the form of phi. The boundary condition says that this thing must be 0. Okay. And so taking together, these tell us that, well, B and A are both 0, right? B 0 comes from here, and this becomes 0. A times L becomes 0, right? We want L to be non-zero because we want the rod to add, or the rod to actually have some length. Okay. So B and A are both 0. So the spatial piece phi has to be identically 0. And so then plug in, right, what we found phi to be in this product solution. we get that this product solution is identically 0, okay? And again, we have the trivial solution, okay? Which is a solution, but it's one that we're not super interested in, okay? So for our purposes, we're going to say, well, lambda can't be 0, because otherwise we're just going to get the trivial solution. Okay. Okay, so what about if lambda is positive? Okay. So if lambda is positive, then it turns out that solutions to that ODE are going to be of this form: cosine of root lambda x or sine of root lambda x. Okay, so the question is, why those? Well, we can go through the same kind of route or same method of using this characteristic polynomial from ODEs. Okay, so all right, for our ODE, d squared dx squared of phi is minus lambda phi. Okay. Assume phi takes this form. Solution, plug it in to our ODE, we get that. Okay. Take this derivative, this r is going to come down twice. Okay. Move this over to the other side, factor out the e to the rx. We're going to get that kind of this product is equal to 0. Okay, and again, remember here, lambda is strictly positive. Okay, so in this case, we must have r squared plus lambda is equal to 0. Why? Well, e to the rx, right? Even if we just draw a picture, looks something like that. This is never 0. Okay. So then we're left with this thing must be 0. And where the roots of that polynomial, well, the roots are plus or minus I times square root of lambda, where I is root minus 1. Or equivalently, I squared is minus 1. Okay. And so this is why we chose to have that minus sign in with the separation constant, because now we can express lambda like this, as opposed to having a minus lambda, but keeping in mind that it's positive. So then the square root is no issue. Okay. Okay, so for solutions to this ODE of this form, R needs to be this, right? So what are the actual solutions? We have two options, right, for each of the roots plus or minus I times root lambda. So for this one, if we use this thing called Euler's identity, we get this expression. Right? For the other one, the only change is that, right, plug in minus there, minus there. For cosine, so cosine of minus x is equal to cosine of x. Minus x is equal to cosine of x. Likewise, sine of minus x is equal to minus sine of x. Okay. So we have kind of these equivalent forms for these complex exponentials. In practice, we're interested in real solutions. Okay, and so what we do is we just take the linearly independent functions in here. Right. So written out, right, the linearly independent pieces that kind of generate these two general solutions we found are exactly cosine of root lambda x and sine root lambda x. Okay, so for our purposes, we're just going to take these two pieces, take linear combinations of those, and say any other solution we can get in this way. And you can also directly check by taking each of these functions, plugging them in for phi, and then verifying that this holds would be another method. Okay, so then for this ODE so for this ODE, we get phi of x is equal to c1 cosine root lambda x plus c2 sine of root lambda x. It's the most general form of solution, where c1 and c2 are constants that are to be determined. Okay, how are we going to figure out those constants? Well, we have boundary conditions, right, that play into phi. Okay. So the two boundary conditions in particular are phi has to be 0 at the endpoints at 0 and L. Okay. So the condition that phi of 0 is equal to 0, well, plug that in. Cosine of 0 is equal to 1, right? Because cosine starts there, goes like that. Sine of 0 is equal to 0, right? Because sine goes like that. Okay. So we have c1 times cosine of 0, which is 1, plus c2 times sine of 0, which is 0. And that leaves us with c1 is equal to 0. So our spatial component is just going to be a sine function. Okay, well, so what does the other boundary condition give us? Well, if you plug it in, right, so here already using that c1 is 0, so we don't have to worry about this term. Okay. And so then what we get is, right, plug in x equals to L. We have this condition right here. Okay. So one thing to note is that we don't want c2 to be 0. Okay. So here what we're dealing with is something times something else is 0. So one of these two things has to be 0. We don't want this one to be 0, because then otherwise we'll have phi of x is equal to 0 times something plus 0 times something. So phi will be a trivial solution, which we're trying to avoid. So c2 cannot be 0. So the only other possibility is that sine of root lambda L, that's equal to 0. Okay. So we have this. Where is sine 0? Okay. Well, in this case, we're going to get that kind of this argument in here has to be a multiple of pi. Why? Well, if we draw a picture, okay, so this is sine of x. Question is, where is it 0? Well, it's 0 at 0, 0 at pi, 0 at 2 pi, 0 at 3 pi, 0 at 4 pi. So for sine of something to be 0, this something has to be a multiple of pi. Okay. And so in this case, n can be positive or negative, right? This graph keeps going backwards. But keep in mind that we have that root lambda. So if we solve for lambda, right, in this case is what we're trying to do, we're going to get lambda is equal to n pi over L quantity squared. Okay. And so already we notice that, well, we have choices for these spatial solutions, right? Depending on what n you plug in here, you're going to get a perfectly valid spatial piece for our product solution. Okay. So this tells us that the spatial pieces depend on n, right? We have one parameter there. As we set it up, we don't necessarily have enough information to figure out what this constant is. But otherwise, the spatial piece is going to be sine of n pi over L times x. Okay. And so putting everything together, right? So we had a constant from the time piece. We have this constant from the spatial piece. Two constants. The initial condition is going to tell us what that constant has to be. So we're just going to kind of group them into one. But the takeaway now is that we kind of know what our building blocks should look like, right? These separated solutions, right? U is equal to phi times G. All these pieces must look like this. At least that's assuming that lambda is positive. So in this case, lambda has to be positive. Okay. So why is that? Well, let's next topic. So what if lambda was negative? Okay. Then we'd be working with this ODE where since lambda is negative, right, minus lambda is going to be positive. Okay. So what we get is that, well, phi has to take this form where kind of, I was saying, right, we wanted the minus sign to avoid kind of this messy root of minus lambda where minus lambda is actually positive. So in this case, minus lambda is actually positive. Okay. But here we have some constant times an exponential of a positive coefficient times t plus a different constant times an exponential of minus positive constant times t. And so this comes around from this characteristic polynomial, right? Same one from above, r squared plus lambda. But now lambda is negative, and so we can factor it in this way. I guess we could have before, but we would have had to incorporate the i's. But anyways, we can factor in this way. So r is either root minus lambda. And again, this is going to be greater than 0 because lambda is less than 0. Or r is equal to minus root minus lambda. So it's the same technique to get these kind of this general form of the solution. So what do the boundary conditions tell us? Well, phi of 0 is equal to 0 tells us that, right, so plugging it in, what was it, here, plugging in 0 here, plugging in 0 here, we're going to get e to the 0, which is 1, e to the 0, which is 1. So that's why we get the C1 plus C2. Technically, it's C1 times 1 plus C2 times 1. Yeah. And then phi of L is equal to 0. Okay. We're going to get something a little more complicated, but not terrible. Okay. So the question is, for this kind of lambda and for these boundary conditions, right, can we figure out what lambda must be or must look like, similar to the previous case? Well, so from this first one, you get that C1 is equal to minus C2. So if we use that and plug it into the second condition, right, so here plugging minus C2 for that, we're going to get this expression. And then if we move things around, or so factor out a C2, we're going to get this expression. Okay. So notice that, again, we cannot have C2 equal to 0. Okay. Because if C2 is equal to 0, then C1 is equal to 0. And so our solution here is, right, this is 0, this is 0. So C2 cannot be 0. So this thing right here must be 0. Okay. So I wrote can't have C2 equal to 0 because that's the trivial solution. So we're left with that's equal to 0. Okay. Move this to the other side. Multiply by e to the root minus lambda L. So we're going to get kind of, so I can write it. So e to the root minus lambda L, e to the root minus lambda L, right? So on the left-hand side, this whole thing is going to be e to the root minus lambda L plus minus e to the, or e to the minus root minus lambda L. Those are going to cancel. So then this 1 is really e to the 0, but anyways. So this is what we end up with. 1 is equal to this expression. Take a log, or say, since we're working with all real numbers, the exponents here have to be the same. So that tells us that 0 is equal to 2 root minus lambda L. 2 is non-zero. So the only other possibilities are either L is 0 or root minus lambda 0. We don't want L to be 0, right? Because we want a non-trivial rod. And so then what we're left with is root minus lambda has to be 0. So minus lambda has to be 0. And so recall, so scroll up a little. Here we were starting with the assumption that lambda was strictly negative. Okay. But what we end up with is that, well, actually lambda is equal to 0. Okay. So in this case, if we assume that, right, lambda is negative, then we get a contradiction. Right? Lambda can't be negative and 0 at the same time. So lambda can't be 0. Or sorry, lambda, well, yeah. Lambda can't be 0. That was the first case. Lambda can't be negative. That was this case. And so what we're left with is lambda has to be positive. And in particular, lambda, we got this was n pi over L quantity squared. Okay. So the takeaway is, well, if we want a product solution, right? What is a spatial component? It's going to be sine of root minus lambda. Should be root lambda. With, let's say here, with lambda positive. G, the time piece, is going to be this exponential in minus k lambda t. And so then lambda is going to be, yeah, kind of this expression, n pi over L squared. And so in particular, we have a bunch of choices for lambda, and therefore we have a bunch of options for phi and g, right, that depend on n. And so what we can do is, well, putting things together, or actually plugging in for lambda, we get that phi looks like that, and g looks like that. Okay. But the point is, right, if we're looking for a separated solution, okay, the pieces are going to look like this, and we're going to have kind of one free parameter that we can choose, n. Right? So we're actually going to get a bunch of these solutions, one for each choice of natural number n. And so what we'll see next is how to kind of put these solutions together and to be able to match them to an initial condition, and then start to actually solve these